Greetings once more. Variation of parameters. That sounds very familiar. We have done this several times, so why even devote a new section to it? Because it's, again, a different way we're going to do this. And it's a little bit more messy. So what is the situation? Again, we are still dealing with these linear second order equations. They look like this, right? In the previous method, a nice guy gave us a homogeneous solution, and using that we reduced the order. In this section, we need an even nicer guy. He needs to give us the fundamental system. Okay, so a nicer guy gives us the full fundamental system. He gives us y1 and y2. This is a fundamental system of solutions of the complementary homogeneous one. Okay, instead of one, he gives two. Now, by the way, we could be the nicer guy if we have a nice guy. Remember from the previous time that if a nice guy gave us one single solution, we could use the method of reducing the order to get the second one, right? So, but of course, then when we do the previous method using one, we got everything. So once we have everything, there's no need to do this method anymore. So you might say, so you might even question, why would you want to do this even if you can do it much better with the other method? The reason is that if you know the more information you need, sometimes the less work you need to do. So it's a balance between how much you know and how much you need to do to get to know the rest. It's somehow a principle that students find hard to accept, is that a particular problem has a certain work cost. There's absolutely nothing you can do about it. To get to the solution of this problem, you have to do amount of work. And there's never a shortcut that gives you all of a sudden the answer, other than cheating, of course. But it needs a certain amount of work. So this method will need a little bit less work, although it's a little bit more complicated. You might not like it that much, but it requires more information, which meant that somebody else had to do the other work, right? Okay, so how does it work? So the formula here, so let me box it again as a formula that we're going to use, is we're going to look at the solution where we're going to, what was the method of parameters? We would say y equals u times a homogeneous solution. The problem is we have two here, so what we do? Well, we take two parameters. That's why there's an s here, a plural, plus u2, y2. Okay? So both u1 and u2 parameters are depending on x. So this was for in many instances, in particular also even for reducing the order, that's what we did, right? Now we do it slightly different. Now, okay. But we would say, okay, but now we have two functions that we have to find. Well, we're going to put one constraint on these functions such that, and it's a bit strange constraint, but I'll write it down, such that u1 prime y1 plus u2 prime y2, okay? So the derivatives, we take y1 and y2. So what you have, when I'm now writing this formula, it's a little bit vague what is going on. I'll do an example right away. But keep in mind, y1 and y2 are given to us. It's not. These are really functions with x's and stuff and God knows what in there. The u's, these are just u's. Okay. So here again we have u prime and u double prime, and these are the same functions as before, and we put this equal to 0. So in other words, this is one condition that we will have. So I'm going to do this in different color because this is why am I in this? Okay, let's do some fancy colors here, right? So, and it turns out, and I don't want to do this in general, just done in the textbook, that if you make the first assumption that the first equation, that the second equation becomes u prime. Now with the primes here, y1 prime plus u2 prime y2 prime is equal to f of x, where f is the forcing function. So let me say we'll see how it works. So what I'm saying is, if we know y1, y2, we're gonna propose a solution of this form, that y that is bound by this u1 and u2, and satisfies these, and we solve this system here. So you see, this is actually a system of differential equations that we're going to try to solve here. So remember, the y's are known now. It's the u's that we're going to try to solve. But how do you solve a system of equations in two unknowns? Well, it's the same thing as a linear system. So you solve for one and plug it into the other and then solve the system. It's much easier if it's much more, it all becomes more clear if I do this on an example. So the example I want to do is here. Okay, we have the system x squared y double prime minus 2x y prime plus 2y equals x to the 9 halves. Okay, so again, this is not constant coefficients, so we cannot use that method. You should be a little bit careful. We have to write it in the standard form here. A textbook uses the other form, but comes down to the same thing, because this f here is the f when you write in standard form. This is not standard form. So if I do this in standard form, I have to divide everything by x squared. So get 2 over x y prime plus 2x squared y equals x to the, what happens here? We subtract 2 from 9 halves. That means 5 halves, right? So this is now in standard form. So this is going to be my f of x in this system. So let's write down the system. But I don't like u1 and u2. So I'm going to use u and v here. Now, you say, okay, but what we do with this? Well, I haven't, the nice guy, where's the nice guy? Hey, nicer guy. The nicer guy hasn't given us the thing yet. The nicer guy comes and says, okay guys, you've been cool, and I'm going to tell you the two solutions are x and x squared. There's a fundamental system of solutions. Of solutions of the complementary homogeneous. Of course, it's always of the complementary homogeneous, the last guy, right? He doesn't like non-homogeneous things. So he says, I can do homogeneous, but don't ask me the non-homogeneous. You do it yourself. Because that's the only thing left, right? If we want to find the general solution of this, we know that it is a particular solution plus a times x plus b times x squared. That's how we know that the general solution looks like. And so now we're saying, okay, I'm going to take y to be, and instead of u1 and u2, I'm going to use them u and v. So ux plus vx squared. That's the solution I'm going to try to find. But I'm not using, now you would say, oh, should I plug in y? No, you don't plug in y here. You go immediately to these equations. You can do that, by the way. And perhaps I'll do it later, but I don't want you to think that is what you need to do. So let me skip this. So now you say, okay, write down these two equations here. Okay, the first equation is where you copy remember what everything is, right? y1 and y2 are x and x squared. So in the first equation, you don't take derivatives, that we take derivatives of the other guys. So we write 0, 0, 0. So be careful. What I'm saying is these equations do not come from this. Okay, what actually happens is this is an equation that I make up, and if you make up this equation, then you get that. But I don't want you to, it's like looking underneath the hood in a car. Let's not do that. Let's just drive the car. Okay, so u prime x plus v prime x squared is 0. Okay, so remember that the first equation is about taking u primes. Now the second equation is also u prime and v prime, but now we're going to take derivatives of these two solutions that we have. So that is u prime times 1 plus, and this here times 2x. And that's not equal to 0, that's equal to x to the f function, to the forcing function. So this is the system that we're trying to solve. Let me write this a little bit neater. U prime plus 2xv prime equals x 5 halves. And the other one is u prime x plus v prime x square equals 0. So what do you do now? Well, there are, again, you think now of, so think u prime and v prime are part of a linear system of equation. So if you want to think in matrix, so now for us the x's are for temporarily, just for a sec, we think of them as constants, and we solve a differential equation, a system of linear equations just usual way, okay, but just temporarily. So we have two methods. The substitution method, you solve for instance here, you could solve for u prime and plug it in this equation. Or you could do the elimination method. For instance, you can multiply this one with x and subtract from this. Because temporarily we're thinking of x as a constant, so we are allowed to do that. Okay? Which one you want me to do? The substitution is the easier one, so let me do the other one. So I'm going to multiply this with x. So x times, yeah, I'm going to write this here. X and x looks the same, right? So I write that multiply with, all right, multiply it with minus x and then add. Okay, so we would here, let me write it here in small. So we have a minus x here, we have a minus, so this one minus 2x squared, and this is then minus x to the 7 halves, right? Okay, so if I add this now, so this is the x minus ux prime here now. Okay, so if I add this, these two cancel. So this is 0. We have here v prime x squared minus 2x squared, so this minus x squared v prime. And here we add this up, this is minus x 7 halves. Okay, see, this becomes easy, right? So this is now a simple differential equation, linear order equation, where divide everything by x squared. So v prime is, minuses also cancel, x to the 3 halves, right? X squared is 4 halves, 2 is 4 halves, so subtract that. So v prime is 3 halves, so v is underdriving, so add 1 to the exponent, that is 5 halves, divide by that exponent, plus a constant. Okay, you have to think a little bit what we do with these constants. So in this case, we don't need a constant. We only need one solution. And so this is why I can take this to be 0. Okay? So we find that v is 5 halves is 2/5, right? 2/5 to the x to the 5 halves. What about u prime? Well, we could now plug this in, right? Let's plug it in the first equation that we had here, which I messed up a little bit with my blue. So that was this one here. So we have u prime was equal to here, this equation, but I'm going to write it a little bit in this way here, bring this to the other side. Okay. And we found that v prime was x 3 halves, so this is x 5 halves minus 2x x 3 halves. Don't take the derivative of this to find that this was v prime, right? Because you have it already, okay? So if I solve for this, that is 5 x to the 5 halves minus 2 times x to the 5 halves, so minus x to the 5 halves. Oh, that's simple now. U is the antiderivative of this thing. So that is minus add to the exponent, divide by it. Again, since we only need one solution, no constant here. So we find minus 2/7 x to the 7 halves. Where are we? We found u, we have v. Where do we go? We go to this guy here. Okay? So we say that y, and this is a particular solution, is u, which was u was this guy, minus 2/7 over 7x to the 7 halves, times x, so times x, plus the other guy, v, what was 2/5 x 5 halves, times x squared. So if I were to work this out, it's minus 2/7 x to the 9 halves plus 2/5 x to the 9/2. So actually they combine here. We see that we get exactly one solution here, one power, and if you combine some like terms, so that's on the common denominator, 35, so that's minus 10 plus 14 x to the 9/2. So this would be 435 x to the 9/2. So now, last step, I forget the numbering here, but the general solution, well, we know the general solution, we need a particular solution, which we just found. This is a particular solution, right? 435 x to the 9/2, and then a general linear combination of the fundamental system of equations that we had here. What was the system of equations? Here, this one, right? Okay, so that's how it works. You see, the calculation is a bit quicker, right? Because you basically, let's do another example to hopefully convince you that the calculations go quicker. So here is another one: y double prime plus 3y prime plus 2y equals 1 over 1 plus e to the x. Again, there could be initial conditions here. Let me see, should I put one? Give me a sec here. Yeah, I'll put in the initial conditions here. The textbook doesn't do it. I can use 0 here. That's not a problem. So I'm not going to run into problems here. I'm concocting one. So give me some time here in my concoction. I'm still concocting. I'm not finished concocting yet. I'm going to put this equal to that equal to ln of 2, and the derivative, that one I won't be able to get so nice. Let's put this equal to, it's not gonna come out that nice, I'm afraid, but okay. No, let me do this 2 times ln 2, okay. Give me a sec, I'm getting on the other one. Well, the other one I'll decide later, okay? Just, okay, let's do. Okay, so, Professor, we need a nice guy. Well, why don't you are the nice guy? Oh my God, what does that mean? So, can we find the fundamental system of equations here? Of the homogeneous, complementary homogeneous? What is the, but it's a linear one. With constant coefficients, that we know. Oh, okay, this is constant coefficients, so we know how to deal this. Okay, Professor, let me do it. Step aside, I'm going to do it. So step 1, here, this is the nice guy, right? I am being the nicer guy here. Let's see what he did. Okay, we know that this is y double prime plus 3y prime plus 2y equals 0. We look at the characteristic equation. That is, not y, t now. T squared plus 3t plus 2 equals 0. The t here doesn't mean time here. That's just a variable that we use for the characteristic equation. So we have to multiply to 2 and add up to 3, and that does the job. So we had t is -1 and t is -2. So we know that our general solution looks like y homogeneous looks like a times e to the minus x plus b times e to the minus 2x. These become the coefficients in front of the power of x. Sorry, in front of x. Good. So now we can do the variation of parameters. And so what we do is we're going to look at a solution, a particular solution. So let me perhaps write by P for the moment here. And instead of A and B, we have now U and V. So that's really what we do, right? We use the same expression, but now with U's and V's. Okay, but we're not taking derivatives here. Now we look at the system of equation. What does the system of equations say? Well, first of all, you take at the same thing, but now you replace U's and V by their derivatives, and that has to be equal to 0. And then you take the derivatives of these guys, which is minus e minus x, and this is minus 2e to the minus 2x. And that is equal to the Forstick function. This is this funny function there, 1 ex. Okay, let's go back here. Let me see where this comes from. This is the pink one, right? And it's you just have to know what this formula says rather than trying to memorize it. It says you take your fundamental system equation and you look at two equations that come from it. You're going to look for this. You look for this solution, and there's two. But what you do is you solve this equation where you replace the u and v by u prime and v prime, and then you take the same equation if you want, the same part here, but instead of that you take the derivative of these guys, and that is equal to f of x. Okay. Okay. So what can we do here? Again, we think we're gonna solve for either u prime or v prime, because we think of this now as a linear system in u prime. So this is a system, a linear system, where linear we have to take, I'll put it between quotation marks, that is thinking of x as a constant, then it's linear system in u prime and v prime. That's the weird part, right? So we can do substitution or we can elimination. Now elimination is better now, right? Because look, these two terms are going to cancel if I add. So I'm just going to add these two, and what I get? Well, this is 0, and then we have here plus v prime, and they have actually basically come down to the same coefficient, right? With a 1 minus 2, so we get a minus 1 here. So let me write it just like that. Okay, so the 0 we saw that, so minus v prime e to the minus 2x. So I repeat, this is just adding these two terms, and these are like terms, so that's the result of that. And that is, of course, adding here too, this is 1 over 1 plus ex. So bringing v prime is equal to minus e to the minus 2x. No, plus 2x, because I'm bringing it to the other side, 1 over x. So v is the derivative of this thing. E2x over 1 plus ex. Where am I? Okay. Dx, okay. Now this integral, by the way, now that I have that, can I find perhaps what is u prime then? Right, so notice that here if I solve this from the first equation, I see that u prime e to the minus x is equal to minus v prime e to the minus 2x, and we just said that this is equal to this guy, right? So this 1 over 1 plus ex. So we can solve it both. So the other one is u prime is equal, now being again the e minus x to this side, so ex 1 plus ex. So we have, so u is the antiderivative of ex 1 plus ex dx. So we have to just do these two integrations. Now this integration, let's do the one on this side first. This is perhaps the easiest one, because if I take, well, easiest, what are we going to do here? When there are such complicated functions, you can basically only do substitution. So we look for an inside function, and that is the denominator, 1 plus ex. Right, it's the best thing I do. I could take just ex, but why? Why not take the whole denominator? Because why? The derivative is ex dx. That's exactly what I have. Okay, so this becomes, if I do this, u equals x ex is just dw. This is dw, so this becomes ln of w. I don't need a constant, so no constant needed. I'll keep writing this a little bit, because you might think, oh, you forgot it, but no, I did it on purpose. And so this is ln w, ln, what was w? 1 plus ex. Okay, that's u. What about v? Well, I just said, the only thing you can do is substitution here. Now the problem is that if I do w is 1 plus ex, that dw is ex dx. And that's I'm sorry, I'm looking here in the textbook and they do this integration in a way that I don't even understand. Ah, okay. Yeah, so this second integral is perhaps something that it's a little bit of a trickery work that you have to do here. As I said, because the e2x there, right? So that is actually ex times ex. That's one way of thinking of it. So yeah, the solution to this one was easy. The solution to this one, I'm going to show you, but I don't want you to think that you need to do this because it's a bit too much of a trick. So the trick here is instead of taking the whole denominator, it works, but it gets a little bit easy if I do it with just. And this time I'm just going to take ex to be the inside function, because let's see what we have then. dw is ex dx, right? So what is the top here? That is ex times ex dx, and in the bottom I get 1 plus ex. Okay, I'm rewriting it slightly to say that okay, this ex dx that becomes dw. And then what does this one become? Well, w. And what does this one become? Well, 1 plus w. Right? So this is a case of substitution where you don't do what you're supposed to be doing. Namely, you have an inside function and everything else is derivative of that inside function. That's not the case here. But sometimes you are in situations like that. So now what do we do in this one? You could say, this is, what do we do? Well, it's a partial fraction, it's a fraction, a rational function, but it is not a partial fraction because the degree of the numerator is 1, and it's the same as the degree of the denominator. In partial fractions, one thing you have to be doing is make sure that the degrees of the tops are less than the degrees of the denominator. If that's not the case, what you do is you do long division. Now, long division in this case is very easy. Let's put it this way. W is the same as W plus 1 minus 1, right? There's still a minus sign in front of all this stuff, so I should keep my minus signs here still in front of it. And so this is dw. Let me go back in black here. So what does that do? Well, w over 1 plus w over 1. So I'm going to divide this and this. This gives me 1, and this gives me 1 minus 1 on w dw. And now I can antiderive that this minus. The antiderivative of 1 is w, the antiderivative of that is minus ln of w plus 1. Okay, so again, we don't have to put the constant, plus not needed, okay? So what we have here, minus w plus ln w plus 1, and what is minus, w was what? W was ex, right? In this case, w was ex, so we get minus ex plus ln 1 plus ex. Okay, let's put it all together. Y, so now we're going to the variation of parameters here. This is the formula that I use my particular solution. So that is, you take u and then multiply, so where is u? This was u here, okay, u. So it is ln 1 plus ex, and I had to multiply that e to the minus x. And then v have to multiply with e to the minus 2x plus minus ex plus ln 1 plus ex times e to the minus 2x. Okay, that's the particular solution, and then the general solution is just these two guys here. Okay, and it makes a lot of sense here to combine these ones, right? The e minus x terms and e minus 2x terms. I don't need to, but let me just show you that if I would do this, let me put the e, and let me put them even in front of them, then we have e to the minus x, and we would have here a plus ln 1 plus e to the x plus e to the minus 2x. So now I'm looking at these two guys. That would be b minus e to the x plus ln 1 plus e to the x. So the way that you write this is not so important, but that is one way of writing it. Okay, and so here we have found the complete solution. Now I had an initial value, so I said y0 So if x is 0, then y was, what do you say, 2 times ln 2. Okay, let's plug that in. So 2 times ln 2. If I plug this in, I hope that it's now makes sense here. E to the power 0 is 1. So we have an a plus, and here we get ln 1 plus 1. So, sorry, ln 1 plus 1, so ln 2. So this is a plus ln 2 plus, and what we get here, e to the power 0, that is 1, plus b minus 1 plus ln of 2 again, right? Oh, ln 2, so the 2 ln 2s, and they cancel with this, so this cancels, and so we get that 1 is equal to a plus b. Okay, that's a nice equation. And so now, for the second, so we also, y prime is equal, and I haven't told you what it is yet, so because I'm going to take something nice. But we did take derivative of y prime, and this is where we have to take derivative of. So that is minus ex, that's taking derivative of the first part, right? And then copy that part and take derivative of the inside part. Now, the derivative of a is a constant, that is 0, and then the derivative of ln that is 1 over 1 plus ex times the derivative of the inside function. Okay, so actually these two cancel. Plus, now I take the derivative of this guy, so that's actually a minus then, minus 2 e to the minus 2x, copy the whole thing inside, and I'm doing the product rule, right? On the second term here. So in case you're not, if you lost me, I'm going to do the derivative of this, copy that. That's the derivative of that, copy that, and now reverse the roles. So plus, right underneath, e minus 2x. Take derivative of this guy, that is minus ex, and then the derivative of this ln is 1 over 1 plus ex times ex. Okay, now this time the e minus x do not cancel. Okay, let's plug in. X is 0. So y prime, so y prime of 0, what is that equal to? Okay, so we have a lot of terms here. We have a minus a plus ln 2, and then the next term is 1 over 2 plus 1 half, right? This is just 1 half. Here I get minus 2 b minus 1 plus ln of 2. And then the last term I get minus 1 plus 1 over 2. Yeah, that's what I get. So that is, this would be, this become minus a half. Oh, these halves and minus a half cancel. So I get minus a minus ln 2 minus 2b plus 2 minus 2 ln 2 minus 2b plus 2. The halves already had cancelled. Okay, so that is what I get. And so let's say for the simplicity, that for make life a little bit easier for us, that this was equal to minus 3 times ln 2. If this is equal to minus 3 times ln 2, then the ln's cancel again. I'm trying to be nice here, okay? So this would be a plus 2b equals 2. I'm bringing the a's and b's to the other side. That's one equation, and the other one was here, a plus b is 1. A plus b is 1. So if I now subtract the second from the first, I get a 0 plus b equals 1, so b is 1. And I plug in the second, then I see that a actually was 0. Okay, so our solution would be plugging in, let me not do that, these two numbers in here. That would be the solution to the initial position. But more particular, of course, interesting for us is to find this is the general solution. And notice that so what I'm trying to say is this is a method that even can be useful for constant coefficients. You might say, but didn't we do this in 5.4? Yeah, but this is not of the form that it's supposed to. In 5.4, so remark, in 5.4, this function, we wanted to be of this form. It had to be an exponential times a polynomial. But this is not an exponential, the exponential sits inside, right? So don't confuse this. You could say, oh, alpha is 1 here. No. This is not ex times something. This is more complicated than that. So that's why we needed this method. Now, again, since we have the general solution. We could also have picked one of these homogeneous solutions, this one, and do the method. So a second remark here, so remark. Reduce order, we could have reduced the order using e to the minus x. That is, in other words, 5.6. We could have used that technique and solve it. Now, you see that these integrals are already kind of a little bit messy. You can imagine that if you do this in the 5.6 method, that would be even more messy. Okay? So, okay, I'm not going to give more examples. I'm going to let everything else for the homeworks for you to do, and then we'll go over them.